a steel connection. Okay? We also have to keep in mind that if we want to design a dissipative structure, the only way we can get some energy dissipation into a timber structure is basically to make sure that the connectors, so nails, screws, dowels, bolts and so on, will plasticize. So for timber structure, since timber is an inherently brittle material, we will be able to get some ductility, some energy dissipation only in the connection system. So only by designing properly the connections to make sure that the metal fasteners are going to plasticize. Okay? And now we start with a carpentry connection. We say a few words about carpentry connections. So, unioni di carpenteria. Of course, those kind of connections were the first that were developed in timber engineering because they are very simple. If you look at all the historical buildings where timber was used, they all have this kind of connections here. Some typical possibilities here. So this connection, depicted here in A, takes the name of half-lap joint. Then this connection depicted in B, it's called step joint. There are also some, to be honest, there are also some Italian names for those connections there, but I don't know them. So I mean, they are not very much used, but of course there are some Italian translations, but I have no idea about it. So just, I mean, if you're interested in Italian translation, try with a translator, but I guess that you won't find it. So you should basically take an old timber book like Giordano, for example. It's an old timber book, and there probably will find all this connection with some specific Italian names. Okay? So as far as they are concerned, of course, I mean, I'm not interested that you learn by heart Italian translation. For me, it's just important that we understand what we are talking about in terms of this type of connection here. So we said half-lap joint, A, step joint, B, very much used for example, for king truss systems, capriate, of course. Then we have this C, mortise and tenon joint. Tenon and mortasa, I think this is the only one that I know in Italian. Tenon should be tenon and mortasa. Kind of masculine, feminine, as you can see here. And then this one, covec joint, I have no idea how this can be translated in Italy. So, when it comes to basically draw and design one of those connections, you just need to keep in mind that typically a truss system is designed with a pin connection. So we usually design a truss system with pin connection in order to make sure the system is statically determinate, and so we can use all the theory that we learned in the course of statics. So you can see that when we talk about the step joint, which is very common for the king truss, we can have the step joint ahead, in front, basically the notch in front, or the notch can be in the heel. So it would be in Italian, this would be the tacco. Or we can have double step, so one on ahead and one on the heel. Geometrically, of course, it will be a matter of decompose our forces into different directions. And of course, when it comes to drawing a joint like this, there are some rules. For example, usually this notch here is cut by making sure that those two angles are the same. So this is kind of a bisector here of the angle. So this is very commonly cut in this way. And also the other member is usually cut on the bisector, but this is not always true. Sometimes this could be cut also to a different angle. But this one, as I said before, on the notch, this is usually cut at the half of the angle. So if this is beta, of course, if beta is the inclination of this rafter, of course here we have that the perpendicular to this inclined line is inclined by beta divided by 2 with respect to the axis of the rafter. So by geometrical consideration we'll find that the segment which is perpendicular to this notch is inclined by half of this angle here of the rafter with respect to the tile. These quantities that we will mention later, h, so the depth of the rafter, and tv is basically the depth of this step, of this notch here, measured vertically. So some general rules. This is a rule that you can find in literature. It's not mandatory, but it's a recommendation. So when beta is less than 50 degrees, then this distance should be less than a quarter of the depth of the rafter. And instead, when beta is more than 60 degrees, this distance should not exceed 1/6 of the depth of the rafter. Now, in terms of design, what kind of verification do you think we need to do in this case? Let's start to think about here. We have a notch, we have a compression force. How do we have to design a connection like this? What kind of failure may occur at ultimately mistake in a connection like this? What do you think?
Compression perpendicular to the grain?
Absolutely, yes. Compression perpendicular to the grain. Well, wouldn't say perpendicular to the grain. I would say at an angle to the grain. Because as you can see here, so here, for example, in the tile, the grain runs horizontally, while instead in the rafter, the grain runs at an angle beta, we said before. So here there will be some pressure distribution, which, as you can see, will be on this face here, will be more or less perpendicular to the grain, not really perpendicular, but more or less perpendicular, while instead in this notch here, the compression will be at an angle to the grain, closer to the, I would say, parallel to the grain, but at a certain angle. So we have compression at an angle to the grain. And of course, for the third principle, principle of action and reaction, also we will have some compression on the rafter. Also here we will have some compression at an angle to the grain on both curving surfaces. So first of all, we will have to check compression perpendicular to the grain to make sure that this does not exceed the strength of timber at an angle to the grain. And then what kind of other failure mechanism you could see here? Suppose that you push a lot here, down here, what could have happened? Well, we have some plasticization in the joint, but there's also another very tricky, even worse failure mechanism rather than compression perpendicular to the grain. If you remember, compression perpendicular to the grain, in the end it's a plastic deformation. It's very hard to get a real failure. I mean, in the end you get lots of indentation, lots of plastic deformation, but you don't have a real failure. Instead here, you could have a real failure if something happened. If you look here, what could have happened in this region here? Remember that the grain of the wood runs in this direction here. So, if you push it out here, what could have happened? Shear failure where? So here, you see here we have a compression. This compression force will have a horizontal component. And since here the grain is oriented this way, on the tile what could have happened? That's here we have a shear failure, longitudinal shear failure along this surface. So if here this surface is this length is too small, then we would have this kind of shearing, which is very brittle and very dangerous kind of failure mechanism. Okay? So, how do we solve the problem? First of all, we have to decompose the force applied along the rafter into the different directions, assuming that this force will act perpendicular to the carving surfaces. So perpendicular to this notch, perpendicular to the other notch. Okay? And if we assume that this is a pin connection, how should the other two components be? First of all, of course, they should be in equilibrium. So we need to decompose this force here in two directions. One is the direction perpendicular to this carving surface, and the other is the direction perpendicular to the other carving surface. So of course, given one vector, and given two directions, the problem is statically determined. We can find, if we know F, we can find the other two components, the other two reactions. One here and one here. Then what is the other condition in order to make sure that this is a field connection and not instead a fixed connection? Once we have decomposed, we have the other two components. What is the other condition to make sure that this system of three forces are in some way obtained into a restate, which is a pin connection? Yes, in order to make sure that the system can rotate, how should those three forces be? First, they should be in equilibrium, this is clear. But in terms of directions, yes, the same plane, but it's a plane structure. So I can't expect those three forces not being the same, because it's a plane structure. So they're for sure they have the effect. But think about, in a system, to be a pin connection, how should be the different directions of those three forces? Yes? To what? No? To make sure that the system, this connection is a pin connection, we need to make sure that those three forces will pass through the same point. Okay? So these three forces must converge into a point in the plane to make sure that this is a pin connection. Otherwise, you would have a bending moment, basically. Okay? So the connection wouldn't be a pin one. So, how can we solve this problem? Okay, so we know this direction, the direction of the force of the rafter, which is basically the axis of the rafter. Then, what we do, we know the direction of the other two. But of course, if we assume that both other directions are going through the middle points of those carving, we wouldn't get to the same point. You see, if you see here, if you take the other direction in the middle point, then they wouldn't join the other two lines in the same point. So what we do usually is, we want it's a conventional verification. We assume that on the front notch here, this force will go through the midpoint. So it will be perpendicular to this notch and will go through the midpoint. Then we find the conjunction, the intersection between those two lines. And then from the other line, we take the other direction, which should be perpendicular to the other notch. Okay? So this is the construction. In this case, as you can see, in general, you will have an eccentricity between this other force and the midpoint of the curve. So now, if I was to ask you what kind of distribution of forces can you expect on this notch here, what would you answer me? So here, what kind of stresses, first of all, you would expect to have in this notch here? Yes, sigma first or tau? Sigma, so stresses, compression stresses. What kind of distribution along the notch? Constant. Why? Because you see, this axial force doesn't have any eccentricity. This is basically a uniformly distributed compression force. If you look now to the other notch, what kind of distribution can you expect in the other one? Here? Linear. And why linear? If you look at this cross-section, what kind of forces you will find on this cross-section?
Secondo la sua eccentricità rispetto alla
So this F second here has an eccentricity with respect to the centroid of the cross-section, meaning that in this cross-section you have not only axial force, compression, but you have compression coupled with bending, compression tensione. Okay? In this case, depending on the eccentricity, you might have two different situations, as you may remember from mechanics of materials. So, if this force here belongs within the third of the length, so inside the third of the middle third of the length, what kind of distribution you would have? So the diagram of this pressure, how will it be? If this is within 1/3 of the width.
senza terzo, cioè nel senso non abbiamo l'alternanza di segno.
No, we will have basically trapezoidal distribution. So we have a big value here and a small compression value here. Now, if this point, this force is applied in the outer third of the length of this curve, what's going to happen there? So, what can we expect?
The neutral axis is tangent to.
Well, if it's tangent here, if it's on the third. But if it's instead like the outer third, where does the neutral axis go? If this one is here, closer here, where does the neutral axis go?
In the.
Here? Are we sure?
No, in the.
No, where? Here. In the left is here. No, can't go there. So, if the neutral axis goes here, what does it mean?
No, in the.
Where?
The plane of F prime.
Here. Now, we're talking about now this section here. So, what does it mean, the plane? It's always the same plane. No, I mean, that does intersect, does the neutral axis intersect this line or not? When this F second goes outside. Here. Here. Okay, that's correct, exactly. So when F second moves towards the edge, the neutral axis cuts the cross section. Okay? Meaning that what we can expect to have in this situation, which is also called as a great eccentricity, as you remember. What kind of stress can you expect in this side here? Tension. Is it possible to have tension here in the reality? No, why not?
Because F prime to compression.
Yes, but here, why can't you have? Globally, F prime is compression. This F second is compression, so global is equilibrium is that. So what would it happen if the neutral axis, as you said before, the neutral axis cuts this cross section here? So theoretically, what kind of stress you should have here? We said tension. But it's possible to have tension there or not? No, why not? Well, let's try to see. Okay, so we said this is F second. So the neutral axis should be somewhere here. So, strictly speaking, you should have something like this. Now, the question is, can we have tensile stresses there? Yes or no? No, why not?
La tensione viene mangiata dal peso sulla scorgere. In pratica quel lembo è già compresso, quindi quando si va a fare la tensione viene mangiata dall'effetto di compressione della parte.
I'm not sure. What you are saying is that in the end here, so what would be the stress distribution of your opinion? Let's see. Trapezoidal anyway. What do you think? No? You should just concentrate along this line here. So, along this line, and to think about it, in this line you have basically a contact between two surfaces. Just forget about the rest of the stresses. Here you have a contact line between two members. This is one member, this is the other one. And the point is, in this is a discontinuity line. So along a discontinuity line, can you have compression? First question. Along a discontinuity line, can you have compression? Yes or no?
Yes.
Yes. Yes or no? I don't know. We have to know something, otherwise we are here. We along a discontinuity line, can we have compression? Transfer of compression? Yes. Everyone convinced about this? Okay, now second question. Along a discontinuity line, can you have tension? Can you transfer tension through a discontinuity line? Yes or no? No. Can't discontinuity. If you have a I see, just think about when you stand on the floor, thanks to the gravity, you have discontinuity between your foot or your feet and the flooring, you transfer compression. But when you jump upwards, of course, you are free to jump, means that you cannot transfer any tension, because it's a discontinuity line. So only based on this concept here you can't have any tension there. The only way you can transfer some tension there would be to do what on those surfaces? Would be to? How, for example? Screws, nails, or glue. Okay? So if now I glue my feet on the floor, they cannot jump upwards anymore. But if I have to glue them. Okay? So here we would have separation basically. Meaning that this is not a possible solution. Okay? What is the possible solution in this case? I think you should have already learned this concept in, again, mechanics of materials, talking about, well, actually also in my course, I think about, we discussed a bit about this, talking about members not resisting in tension. Concrete, for example, or masonry or ground. The stress distribution at the interface between a foundation and the ground underneath. Okay? So, here's something like this. And you have here axial force, then you have a set weight of the foundation, and you have a bending moment M. You compose all of them, you find that your resultant is here. What is the stress distribution underneath the floor, underneath the foundation? I'm sure that, I'm not sure 100%, no, I'm almost sure that someone taught you how to design this. How do you design this situation? So foundation with, let's say this is the total force, P plus W as an eccentricity with respect to the base of the footing. So in this case, how can you solve the problem?
Sono compressione, abbiamo le leggi di indicazione.
Yes, but can you have tensile stresses there at the interface between one foundation and the soil? Yes or no? But did you ever see this problem, or was the first time? First time. But foundation, maybe you still haven't done the course next year. In geotechnical, you don't study. Okay. Masonry, of course, you haven't studied masonry because masonry is second year also. Masonry construction, muratura. But in mechanics of materials, I'm sure that you studied this case.
Solidi non reagenti a trazione.
Beh, bravo. Solidi non resistenti a trazione. So if you have the compression and bending on a member which is not resisting to tension, and if your center of pressure is outside what is called the kernel or snocciolo, this would be 1, 2, and 3. Like this. So if this one is outside, theoretically your neutral axis should be here. So theoretically you should have something like this. But we said this one is not permissible because unless you put a pile here, otherwise the soil cannot take down the footing because it doesn't have any. It's not glued to the base of the footing. Okay. So in this case, how can you solve the problem? Solidi non resistenti a trazione. Very simply, you say, okay, I will find a situation of equilibrium where if this is called U, then this is another U and this is another U here. You will find let's do this way. This is P, this is sigma max. So, from the equilibrium, sigma max times B times 3U equal to times 1/2. So it's the area of the triangle basically equal to P. So sigma max equal to 2P divided by 3BU. Okay? So basically you find out a distribution of forces which are in equilibrium with the P, the compression load applied, without taking into account any tensile stress. Are those two systems in equilibrium? Why are they in equilibrium? Because if you see, this is the result of this triangle is basically has the same direction and the same position as the applied load P. Okay? So in this case, if this force F is outside the kernel of the cross-section, then in this case you would have to consider a solution like this, okay, by ignoring the presence of tensile stresses for the simple reason that no tension can be transferred at the discontinuity line between two different members. Okay? Is clear this? I mean, this, I'm sure that you have already studied this in mechanics and stuff. Okay, so we said before, we need to find out first the equilibrium by considering those two directions. This angle alpha, so the inclination angle of the notch is, for geometrical consideration, equal to beta divided by 2. And then we can write the design inequality along the notch, along this notch here. So let's go to have a look how this design inequality writes or reads here. So along this surface, we need to calculate sigma C alpha D. So sigma C alpha D is the compression stress at the notch at an angle alpha to the grain. So, if you look at this notch, consider first the stress distribution on the tie beam. So this tie beam, we said that here we have a perpendicular to this surface here, we have this force F prime applied in the middle. So for the equilibrium here, you will have a distribution of uniformly stresses, which are called sigma C alpha B. Okay? So sigma C alpha D, those stresses are calculated basically by dividing F prime, so the force F prime, by this, the area of this notch. The area of this notch, if we call TV, this size, if this is TV, the inclined surface will be TV divided by cos alpha, where alpha is this angle. Okay? So this would be F prime divided by TV divided by cos alpha times B, where B is the breadth of the tie. Okay? What do we need to compare this stress with? We need to compare this stress with the compression strength of timber at an angle to the grain. Which angle to the grain? Well, the grain in the tie is horizontal. So this is the grain in the tie. Okay? So, if the cut was vertical, since this is the grain of the grain, if the cut was vertical, what should we compare sigma C alpha D with if the cut was vertical? With? FC0D. Compression strength parallel to the grain. But since you see that notch is cut at an angle alpha with respect to the vertical direction, then we need to compare with FC alpha D. Design compression of wood, of timber at an angle alpha to the grain. Okay? Now, if you look back to the lesson about beam state design, where we were talking about compression and angle to the grain, you will find another formula. You will find what we call as the Hankinson equation, which was a slightly simpler equation compared to this. Now, some recent studies and experimental research performed on this kind of connection show that the use of this Hankinson equation leads to two conservative results. So it would lead to oversize of the structures. Since very often we have to use these formulas not for new construction, but to check the stability of existing construction, the problem was that by using this Hankinson formula several times, we would have to change existing king truss. For example, in beautiful churches, this existing king's truss would not satisfy this Hankinson equation. While instead they did some experimentation, find out that they were okay. So for this reason, now they are changing the Eurocode, as I said before, and in some years we will have a new version of Eurocode 5, and they will add also one section about carpentry connections. If you look now, there is nothing about carpentry connection other than this Hankinson equation, and they will propose this new formula that I added here, which is basically a less conservative equation for estimating the compression at an angle to the grain in this kind of connections. So, this equation here is obtained by using the quadratic iteration criterion instead of the linear iteration criterion, adopting the Hankinson equation, which is shortly something about this. Take into account also the effect of the shear stresses and introducing a calibration factor for the experimental results. And then in the end, what they did, they extended the Hankinson criteria by taking into account the shear stresses and by using quadratic interaction rather than a linear interaction, which is less conservative. And then anyway, they added those factors too in order to make this model closer to the results of experimental tests. Okay? So if you want, you can regard this as a kind of semi-empirical equation to estimate the compression resistance of joints like this. Okay? So, the Hankinson equation, the one that you can find in the Eurocode 5, is basically based on this hypothesis here. So, if you have at the same time compression parallel and perpendicular to the grain, the safety can be checked by using this linear interaction criterion, which means basically that example, like here we said before, you have some stresses in this way. So those stresses, so this is the grain. Those stresses have one component parallel to the grain and one component perpendicular to the grain. So we have, let's say, a sigma T0, stress of parallel to the grain, and sigma T90, stress perpendicular to the grain. In this case, the interaction criterion of the value of the Atkinson equation is that if this is, let's say, sigma T0, and this is sigma T90, this is Ft90 and this is Ft0, we will use a linear interaction criterion like this, meaning that if our component sigma T0 and sigma T90, those two components gives a point underneath the line, then no failure occurs. Okay? This is more or less, if you want, like what we were doing in reinforced concrete design when we were going to draw the M&M interaction curve. In this case, we have not an M&M interaction curve, we have a sigma T0, sigma T90 interaction curve. So in each point of the timber, I can calculate the two components, sigma T0, so sigma parallel to the grain, and sigma T90, sigma perpendicular to the grain. If those two components are underneath this line, then our structure is safe. Okay? This is to consider the interaction between the two. So, for example, you see here, in order to derive the Atkinson equation, you start from a single piece of wood subjected to an axial force Fc, applied to a certain angle alpha to the grain. In general, when you insulate a small cube of this wood, you will find that there are some perpendicular components, there is one parallel component, there is one shear component for the equilibrium. Now, if you write down, again, this is the small element subjected to an axial force as an angle to the grain. If this is the height of this timber member, you can find out the length, which is perpendicular to the grain, and the length P, which is the one parallel to the grain. And of course, you can also decompose this Ft alpha or Ft R in one component perpendicular to the grain and another component parallel to the grain. So now we should write all this trigonometric relationship between basically H, P, and alpha, and also between the forces. And then you will find that here, for example, sigma T0 should be the sigma acting parallel to the grain. So it would be Ft0 divided by B. Sorry, B is the breadth times Q, which is the sigma that acts in this direction here. You do some substitution now. I don't want to go into too much details about this. It's a typical exercise of structural mechanics, I would say, where in the end, by making some sort of substitution here, you end up with this criteria, which is the Hankinson equation. So this is the equation that we mentioned some time ago when we were talking about design or strength verification at the angle of the grain. So this equation here, you see Ft alpha. So the strength at the angle of the grain is Ft0, the strength parallel to the grain, divided by the ratio between the strength parallel to the grain, the strength perpendicular to the grain, times sin square alpha plus cos square alpha. So this relationship is based on this linear interaction criteria we said before. Okay? So starting from this linear interaction criteria, we get to this equation here. However, as I said before, this linear interaction criteria is very conservative. They found out that by using this equation, we would have to remove most of our king cross system which we have in our old churches, because they will all be not checked for arithmetic mistakes. But of course, we know that they are there for hundreds of years, nothing happened. So we did some experimentation and find out that this criteria is too conservative. So how can we make this criteria more realistic? First, they extended this criteria by using also shear. So you see, they consider not only the linear interaction between the axial force parallel to the grain, axial force perpendicular to the grain, but also the interaction between shear forces. Tau divided by Fv. So tau is the shear, and Fv is the strength resistance shear. And then you see that the Hankinson equation changes to this new relationship. And then what they did also was to use a quadratic rather than a linear interaction. What does it mean, a quadratic criteria? It means basically to replace this line here with a line like this. So to use it, this will become an ellipse. You see? Quadratic interaction. So with this quadratic interaction, we get to this relationship, which is still not the one that will be implemented in the new Eurocode. The one that will be implemented in the Eurocode has a factor of 2 here and a factor of 2 here. And those factors of 2 were introduced at the denominators to fit this equation on the experimental results. So if you want, this has become a kind of semi-empirical relationship. So, this in order to design for compression. Just remember that, strictly speaking, you have to check the compression you have to do 4 compression checks. So, since you have 2 notches on 2 members, so 2 by 2, 4. So you need to do first to check the notch of the tie beam, the front notch of the tie beam. Then we need to check the other notch of the tie beam, and then we need to check the notch of the rafter, and then the other notch of the rafter. So you have to do 4 verifications, okay? Compression perpendicular to the grain on 4 surfaces. Remember also that for this surface here, we said before, in general, we don't have only compression, but we have compression and bending. So we need to do transformer, as we found before, in order to find the maximum sigma C alpha D. So sigma C alpha D is not only F second divided by A, but it's F second divided by A plus the moment contribution will be F second times E divided by the section modulus. Okay? And then we need to do another control, the shear verification along the lead surface. In this case, we need to decompose F into components, one component horizontal, one vertical. The horizontal component is F times cos beta. And then we need to make an assumption regarding the distribution of the shear stresses along this surface. The assumption is usually the uniformly distributed one, for the sake of simplicity. However, we need to keep in mind that in the reality, the shear stresses are never uniformly distributed. Usually they have a peak at the beginning and the end. And for this reason, the derivation said that we can use the uniformly distributed hypothesis only up to a length not exceeding 8 times TV. So if TV is this thickness here, we multiply TV by 8, and if this length here is higher than 8 times TV, in the formula, to calculate the tau, we need to put 8 times TV. So basically we can consider in the calculation of the shear stresses along this surface, surfaces longer than 8 TV. So we can consider, of course, surfaces longer than 8 TV, but not in the formula. The formula we need to take, if we have a surface here which is length 12 TV, in the formula, we need to put LB equal to 8 TV. So this is the maximum that we can put inside here to calculate the shear demand. So the shear stress demand, you see, is the shear force, so F cos beta, divided by LT with the limit of 8 TB, as we said before. TB is this distance here. Times KEF. KEF is this crack coefficient that we heard about when we were talking about shear. So this coefficient, which is equal to 2/3, which takes into account that due to cracking in solid timber, also in glue gum, we will have a narrower resistive cross section in shear at least. So this stress will be compared, of course, with the desired shear strength, longitudinal shear strength, calculated as usual. Okay? So those are the verifications to do in this carpentry connection. Now, just to show you an interesting new applications, based on some recent studies, they found out that this kind of multiple step joints has an excellent behavior. So it's much better to have a multiple step joints than only a single step joint or a double step joint. In this case in particular, you can see that they have a kind of glue laminated timber beam where they use for the outer lamination hardwood, so very strong wood. This way, of course, you have an even better behavior because all this compression perpendicular to the grain will be resisted by hardwood, which has a much stronger strength, compressive strength perpendicular to the grain compared to the normal glue, to the normal softwood. In other photos, with multiple step joints, and here some experimental tests. You can see that, yes?
La formula precedente il campo elettrico tenendo conto delle fessure che si possono verificare
Chi è lo sforzo?
però per quale sforzo? Sempre di flessione come questa di limite.
No, this one was for the shear. This cracks, they are not cracks due to bending. Those cracks usually are cracks due to shrinkage. Fragiacomo. So there are natural cracks that forms when wood dries up. So some cracks open, those cracks are usually horizontal, and they are going to reduce the resisting cross-section in shear. Remember that for shear, the resisting cross-section is the horizontal one, not the vertical one. Because the vertical plane we can't have a shear along a vertical plane because in this case the shear should break all the fibers, which is not possible. So if we have failure, we always have failure horizontal. Okay? I was saying before they did some experimental tests in Germany. Same configuration, so same mode if you want. In one case they use a single step, same cross section, one single step, double step and multiple step. As you can see, the double step is much better, and with the multiple step, the strength is more or less the same, but the results are much more tougher. So the behavior is better. In this case, the design is quite simple. You can see here some formulas. So, the design compression force acting in the rafter is decomposed into a vertical component to a horizontal component. The vertical component is used to calculate the compression perpendicular to the grain that you have, or the angle to the grain that you have inside here in the wood. Using this formula here, and the horizontal component used for the verification of the shear capacity with this other formula that we find here. Okay. Any doubts or something that we want to clarify about the work we saw so far?
This slide. So I have one step, two steps, or multiple steps.
More or less the same strength, but much higher activity. Using hardwood is basically to increase the strength. The problem with the hardwood is that you see, like in this case here, only the external lamination was made by hardwood, not the whole thing. So if you have only the external lamination made of hardwood, it's much easier to have a step like this than the other one. The other one is going to be more, it's going to cut much more of the hardwood here. So with a multiple step, you weaken much less the cross section of the tile compared to the multiple step. So the multiple step, you see, you weaken only just a little bit. Instead, with the other one, you will weaken much more. What? No. This one was to even get much better results compared to the normal one. And the other comment was that this hardwood here is usually only one lamella. Now in this case it's a very thick lamella, but if it was a normal lamella 4 cm, this lamella would be cut with only one step, because the one step is much deeper here. So it would cut completely the lamella. When instead with this multiple step, it doesn't cut the lamella because they are more and shallower than the other one. Più sottile. Okay? So this one.
And this is much expensive than the simple cut.
Well, if you have to do by hand, it would be much more expensive. In fact, in the past they didn't do this because it was much more expensive to do by hand. But today, nowadays, all these connections here are made by machines. They are machine cut. So this one costs exactly the same as the other one in the end. If there is the machine or a robot doing this, you don't care. Maybe it will stay maybe 1 minute, 2 minutes more, but who cares? That's the reason why recently we have more and more kind of concepts that in the past were not used because they were too time consuming or too expensive, but now with the machine cutting it's much easier. Okay? Okay, so now I think we can go back to conclude our roof design. Okay?
For the design I have interconnection.
Yes.
I think some
Okay, now, strictly speaking, I would say now, in terms of regulation, we should use Hankinson. However, we know that this other equation is much better. So my recommendation would be, you should first start with Hankinson. If Hankinson is fine, then okay. If instead with Hankinson you cannot get the verification satisfied, of course, if you are working on a new structure, it doesn't matter. But if you are working on an existing structure, like a structure which is protected, I would say don't go there and say that because of the Hankinson equation you have to destroy the structure to do something. Use the other one. If with the other one, this one that I suggested before, everything's fine, then you can quote this as this is taken not from me, it's taken from a book by Hans Glass, the one that you found on the internet. You can quote for sure this book and say that this will be the base of the new Eurocode that are about to be approved. Okay? Okay, so this is what we are missing here to complete the design, the roof, so the rafter tie beam connection. So we will start from the geometrical properties of the connection. Then we will do the ultimate limit state design of compression of the angle to the break. The other ultimate limit state design of longitudinal shear, the tie beam. Then bearing strength on the column, and then last but not least, couple tensile force and bending moment in the section of the tie beam weakened by the connection. So ultimately state. So starting from the geometrical properties of the connection, we will use a simple Carpenter connection. Those are some geometrical properties. You see here that the notch was cut exactly halfway, the total angle here, 75, 75. While instead you see that in this case, the other carving was not cut at half the inclination angle of the rafter. So this is 10 degrees inclination rather than 30, rather than 15. So we have those two angles that we need to consider for when we are going to do our ultimate state control. So alpha 30 degrees and beta 10 degrees. In this case we call TV prime the inclined length of the notch. So TV prime is 125 millimeter. And we call TL the inclined length of the other surface, of the other notch. TL is 700 millimeter. Of course, when we draw one of those carpentry connections, it's very important to take all the measures because they will then be useful to do all the verifications. We see before some recommendations for TV prime is the inclined length. So TV, the vertical one, which will be TV prime times the cosine of 15 degrees, should not exceed 1/4 of the breadth here, the depth of the rafter, for alpha angle. Basically, this beta here is not the alpha angle. This beta comes from the other drawing. So this beta is actually the alpha. So maybe it could be better if to change, not to make any confusion. Change this into alpha, please. So we don't have it here. This is a copy and paste from the other presentation, but this one was actually called beta. So in our case, we are alpha 30 degrees length and 50, so this one should be no more than 1/4 of the depth. If you replace, you find out that in this case, this TB is more or less 1/3. So it's actually more than 1/4 of the depth, more or less the same.
Ma le superfici sono uguali.
Which one? No. So this one is 10 degrees and this is 15. So they are almost perpendicular but not completely perpendicular, because this one you see beta 10 and this one is 30 divided by 2, which is 15. So they are not perpendicular in this case. Okay? I would say if you have to design a new one, my recommendation is to do this one along the bisector. So in this way it gets perpendicular. Okay, now compression and angle of the grain. Here you have all the geometrical properties, alpha, beta, 1 and 2, and so on. So in this case it's very important to be confident with the trigonometry. So you see this is the axial force N acting the rafter, which is inclined by alpha with respect to the horizontal line. Then we have to decompose this axial force into two components. One component, F1, is perpendicular to the notch, to the front notch. So the F1 is basically inclined by alpha divided by 2 with respect to the horizontal line. And then the F2 line is perpendicular to the other notch, which is inclined by beta. So in this case, you see the F2 is inclined by beta with respect to the vertical line. So, in order to do the verification, we need to calculate F1 and F2. Now, F1, how can we calculate F1? So F1 is the compression force acting perpendicular to this notch here. And this notch here is inclined by 15 degrees with respect to the vertical axis. So, to calculate F1, you see, if you consider this triangle here, this is a rectangular triangle. So we could say that F1 is equal to N divided by cos of alpha divided by 2. So this line here is, you see, inclined by alpha divided by 2. So if you multiply N times cos of alpha divided by 2, we get this length here, from this point to this point. Okay? So this would be N times cos alpha divided by 2. This is the length from this point to this point. And then to get F1, we need to subtract the length from this point to this point here. This length here, how can we calculate it here? Well, if we do, you see this one, if you again, we consider this triangle, this is a rectangular triangle. So this one, this short side here, if you consider this other rectangle triangle here, this one will be this length here times tangent of this angle here. So this angle here, since this is alpha divided by 2 and this is beta, this angle is alpha divided by 2 minus beta. So this length will be this length here times tangent of alpha divided by 2 minus beta. Now, this length, this one, if you consider the big triangle, this length would be n times sin of alpha divided by 2. So n times sin of alpha divided by 2 times tangent of alpha divided by 2 minus beta. So we need to be a bit careful on considering all the angles in this triangle here. Okay? So this is F1. Then we need to calculate F2 for the verification of this surface here. So F2 can be calculated by dividing this. Again, this is a rectangle triangle. So by dividing this side here by cos of alpha divided by 2 minus beta, we get this length here. And this length here already before was calculated as n sin alpha divided by 2. So in the end, F2 is n sin alpha divided by 2, which will be this length, divided by cos of this angle to get F2. Okay? And then we need to start doing our verification ultimately instead of compression at an angle to the right. We need to sketch, you see, the forces. We said before that this force here is applied along the axis of the rafter. Then the reaction from the front notch is taken perpendicular to the line of the front notch, is passing through the midpoint. So by intersecting those two lines we get this point, and from here we take the line perpendicular to the other notch below. And if you see, this other line doesn't pass as expected through the centroid, this cross section. So there is an eccentricity. Yeah?
Did not give first on to
This one?
It's
Yes, you're right. This should be TV prime. It's correct, yes, TV prime. This is TV prime divided by 3. So, if you sketch this, we will find that this F2 is basically applied on more or less 240 millimeter, which is more or less 1/3 of the whole length. So, if this force is applied to 1/3 of the whole length, what does it mean in terms of stress distribution? Triangular, where here the value is 0, and here the maximum value. Okay? So the eccentricity, you see, is 110, so the total length here is 700 millimeter, divided by 2, 350, so basically 110, which is less than TL divided by 6. So it's a little bit inside the third of the length. So eccentricity 110 millimeters. So this is the distribution of stresses at the two curved surfaces. So Then we start by doing the ultimate unit state control of compression and angle to the grain on what we call carving line. The design compression force in the principal rafter is 91.0 kN. The design tensile force in the tie beam is 63.0 kN. So F1, which is the compression force applied perpendicular to carving 1, by using the formula that we saw before, is basically 86 kN. Quite big. And it's perpendicular to carving 1 in the middle of carving 1. Instead, F2, by using the other formula, is 24 kN. And it's applied not right here in the middle, but if you remember, it's applied at the third of the breadth. So perpendicular to carving 2 and at an eccentricity of 110 mm from the middle of carving 2. Now verifications. Sigma C alpha prime D equal N over A less than FC alpha prime D. So compression and angle to the grain, you see that in this case we have used the Hantison criterion, which is the one that we can find on the regulation. So, FC0D is the design strength, design compressive strength parallel to the grain, and we found by using all this equation, 10.8 Newton per square millimeter. FC90 is 1.32 Newton per square millimeter. K6 is 0, Kc90 is 1, sorry, K6 is 1, Kc90 can be assumed equal to 1. So, carrying 1, TV prime, which is the inclined length of the notch, is 125 millimeter. B is 200 millimeters, the breadth of the carving area. F1 is 86 kN, the compression force. Alpha prime would be basically this angle here. So 15 degrees on the side B. And on the principal rafter is exactly the same. So, because you see the principal rafter, this one, alpha prime, alpha prime. So this is the grain along the tie, and this is the grain along the principal. So in the end, in both cases, we have the same angle, alpha prime. Okay? Meaning that since the contact area is the same, in the end, we can make only one check. Because basically by checking, for example, the tie, we are also checking the rafter, if we assume that both have the same strength. Okay? So we replace now the number in the formula, so F1, 86 kilonewton times 10 to the power of 3 newtons, divided by 125 by 200. So 3.4 megapascal. So this stress here at the interface of the front notch between the rafter and the tie is given by 3.4 megapascal. Now we need to compare this strength demand with the actual strength. The actual strength, if we replace inside here the numbers, we get 7.3 megapascal. So you can find that the verification is satisfied because the strength demand is 3.4 kilonewton and the strength capacity is 7.3 megapascal. So, sorry, 3.4 megapascal, and the strength capacity is 7.3 megapascal. Okay? So this is also the order that I suggested before to do. First, you check with Hantison, If Anki is only satisfied, then you can stop there. Of course, you don't need to go on. In this case, I went on just to show the differences with the other relationship. So, if we use the quadratic approximation we see interaction suggested for the step joints, you would get, instead that you see 7, what was before? 7.3, you will get up to 9.1 megapascal. So the other one is less conservative. Okay, now we need to go to check the other curve here. So the other surface. In this case, we already calculated F2, the value of 2. And we need also to understand along this surface what is the inclination of the force with respect to the grain in the rafter and in the tie beam. So the length of the carving is 100 millimeter, the breadth is 200 millimeter, the force is much lower, this time 24 kilonewton. We have an eccentricity to take into account 110 millimeter. And then we need to calculate the angle, so the inclination of this force with respect to the grain of the tie beam. So, go back. Sketch. So, we are interested in calculating the inclination of this force F2 with respect to the angle of the tie beam. So, with respect to the horizontal. Now, what is the value of this angle here? Well, this value here is, as you can see here, alpha. So, this angle here is alpha. Then this value here is 90 degrees minus beta, and this angle here is alpha prime 180 degrees, so everything, minus 90 minus beta and minus alpha. So beta plus 90 degrees minus alpha. So here again you see we need to look a little bit with some attention to the values of the angle here in order to find out the inclination of the force with respect to the angle of the tie beam, with respect to the angle of the rafter. So the angle alpha prime of the inclination F2 with respect to the angle of the rafter is beta plus 90 degrees minus alpha. What is that inclination of F2 with respect to the angle of the tie beam is 90 degrees minus beta. So, for the tie beam, we need to use the formula that we said before. So F1 divided by BT1 plus F1 times Z divided by, so this is TL, sorry, BTL squared divided by 6. So if we replace here the numbers, we get 0.3 megapascal, which is very low value here. The strength, Fc alpha prime D, by replacing the value, which is 80 degrees. So alpha prime for the tie beam is this value that we found before. To go back, alpha prime is 90, 180 minus 90 minus beta minus alpha, so we get basically 70 degrees. And 80 degrees. So 80 degrees on the tie beam and 70 degrees on the rafter. So again, here those are the results. So on the tie beam, 0.3 megapascal of strength demand and 1.4 megapascal of strain capacity. Instead, on the principal rafter, 0.3 megapascal, the same demand, and 1.5 megapascal, the strength capacity. Because as you can see here, the alpha is slightly smaller, 70 degrees rather than 80 degrees. So also in this case, you see that the verification is satisfied. So this is the summary of all the ultimate limit state verification in carbon 1, both type B and rafter, carbon 2 type B, carbon 2 principal rafter. Okay? Then we need to move to longitudinal shear type B. So we need to check that the ultimate limit state of longitudinal shear is satisfied along the surface. We need to calculate this horizontal component of the force and CD, which we can call HD. Consider L mean as the length of verification. So for the horizontal equilibrium, HD will be F1 times cos of alpha divided by 2. So 86 times cos of 15, 83.1 kilonewtons. So the verification is tau d less than FPD. Tau d is the max design shear stress, FPD is the design shear strength. So tau d will be HD divided by KF times P times LB. So HD is 83,100 Newton, KF is 2/3, B is 200, and LB could be our unknown. So we can go to invert this design inequality in order to find out the minimum value of this distance such that the ultimate limit state design is satisfied. So in the end we get 623 divided by MB. We assume K mod 1.9, K6 1.0. Then FPK is 3.4 Newton per square millimeter, gamma M is 1.5. So in the end, FPD is 2 Newton per square millimeter, and this is the design inequality. 623 divided by M mean less than 2 Newton per square millimeter. So L mean should exceed 623 divided by 2, so 312 millimeter. 312 millimeter is less than 8 TV prime cos alpha divided by 2, which is 966 millimeters. So this one is the right result. So we need to have basically a length of at least, a length of at least a length of at least 302 centimeters more or less in order to have this shear verification satisfied. Okay, another design we need to do is the bearing strength that manifestation perpendicular to the bearing underneath the tie beam. This is the system that we saw last week. The external reaction here, the vertical external reaction was found to be 72.4 kilonewtons. So we need to check that this design inequality is satisfied. So sigma C90D must be less than KC90 times FC90D. RD we said is 72,400 newtons. A, the contact, the bearing area will be the breadth of the beam, the tie beam times LBF, so effective bearing length. And LB is our unknown. So we need to know how wide must be the column in order to make sure that we don't have bearing, problem of bearing at the interface with the king truss. So sigma C90D is DD divided by D times LBF. The effective bearing length, if you remember, according to the Eurocode, we can take up to 30 mm more on the right, 30 mm more on the left. So in our case, MDF will be the actual breadth of the column plus 30 plus 30, so maybe plus 60 millimeter. So this is our situation. We do this ratio, TD divided by B times MB plus 60. We calculate the design value of the stress perpendicular to the length, 1.32 Newton per square millimeter. Kappa C90 can be assumed equal to 1. So in the end, we see the design inequality 72,400 divided by 200 times MB plus 60 less than 1 times 1.32. In the end, we can isolate LB. We found out that LB must be greater than 274 minus 60, so 214 millimeter. So in the end, in order to get this ultimate limit state of bearing strength satisfied, we need to have a breadth of the column of at least 214 millimeter. Okay. Now the last check that we have to do, since when we go to do a connection like this, we are going to weaken the tie beam. We want to cut the notch within the tie beam. We need to consider the fact that due to this weakening, we will have first that the resisting area will be less for the tensile verification, and second that we will have an eccentricity in the viscous cross section between the axial force and the centroid of the weakened cross section. So we will have, strictly speaking, tension and bending, okay, due to this notch. So we want to do this verification of coupled tensile force and bending moment in the section of the tie beam weakened by the cross section, which is ultimately mistaken. The design tensile force is 63.0 kN. This is the tie beam section, 200 by 360, and this is the weakest part of the cross section, HW 240 mm instead of 360 mm. So the bending moment that we have is ND times the eccentricity. The eccentricity is H divided by 2, so 360 divided by 2 minus HW 240 divided by 2. So we have 60 mm of eccentricity. So in the end, you see we have 3.8 times 10 to the power of 6 Newton per millimeter of bending moment due to the eccentricity in the weak cross section. So for beams loaded in tension and compression, coupled tension and compression, we use again this linear interaction relationship. So we need to calculate the maximum design tensile stress due to axial force, compare with the design tensile strength, and sum at this ratio, the ratio between the pure bending stress and the bending strength. So cross-sectional area 200 by 240, because this is the reduced cross-section. So 4.8 times 10 to the power of 4 square millimeter. Sigma T0D is ND divided by 8 to 1.31 Newton per square millimeter, and the cross-section modulus B times HW square divided by 6. So 1.92 times 10 to the power of 6 millimeter cubes. Then we calculate the design tensile strength parallel to the grain, which is say Newton per square millimeter. So that sigma MYD, so the pure bending stress, is 2 Newton per square millimeter. FMYD is 10.8. So you see the interaction criterion provides a coefficient which is 0.40 and is less than 1, meaning that also this tie verification of argument mistake considering its eccentricity is satisfied. So this is more or less concludes this work example of a roof design. This was basically a work example that I did first in the engineering course, and I got some help from one PhD student to put, because at the beginning we did everything on the blackboard, and then we got some help from this student here. Some of you may know him, because about studying his PhD here in L'Aquila, to put together this presentation. Do you have any